A pitch shifter is a sound effects unit that raises or lowers the pitch of an audio signal by a present interval. So, for example, a pitch shifter set to increase the pitch by a fourth with raised each note 3 diatonic intervals above the notes actually played. Simple pitch shifters raise or lower the pitch by 1 or 2 octaves, while more sophisticated devices offer a range of interval alteration. Pitch shifters are included in most audio processors today. Time stretching is the process of changing the speed or duration of the audio signal without affecting its pitch. The objective of this project is to implement pitch shifting in Python language. This project can be used for basic uses of pitch shifters that are already in existence. It can either make the pitch of any WAV file higher or lower without changing the speed. So to do our objectives, we use pitch changing function and another function for resampling the WAV file back to its speed and duration. So here now I'm going to explain the codes of pitch shifting. So the library that we used are Sys, NumPy, SciPy, Wave, and Matplotlib. So I'll discuss first the first function, which is the pitch. So first function is pitch. So setting the change rate that will be multiplied to the rate that can change the pitch of the WAV file that we use. So here we set channels, the sample width, the title of the WAV file, and it will be read, and the rate get the which is the 44,100, the signal that will be extract raw audio from WAV file. So this returns the sampling frequency, the change. So we set the change rate in any of these numbers. So 3 for the high pitch, 1 for the low pitch, 2 for the original if you wanted to check, and there. So the final file name for the shifted WAV file is shifted.wav, and it will be right and automatically saved to the folder that you used. And then this is the parameters set. We set these parameters. That's the part of the changing the pitch of the WAV file, but the time still follows it. So the next is the second function is stretch. The change rate here is the change rate set on the burst function, which is the pitch. So window seconds is 0.1. 0.1 because here the original sample has window segments. So per window it has 16 bits, and here the steps wherein it is a compressed sample, so it has a step of 4 steps. So for each window segment, so here is the one window. The range of one window is from negative 1 to 1, negative 1 to 1. So when you stretch it, it will be divided into 2, the window size, and since it's negative 1 to 1, so here is 0. So the start of the new window size will be 0 to 1. So, and it says that the lower the value of the window segment, the good the quality of the audio of the WAV file that you're going to transform. So here, the range here is 0 to 0.5 and 0 and 1. So the window size that used in the program is 0.1 since it is the lowest, and 0 cannot be used because it is the starting point of the window size. The window size range will be 0.1 to 0.5 only, and the rest cannot be used. But you can try it if you want and see the result. And here we set the shifted WAV file, which the WAV file that we already shifted in the function pitch into a sample rate and SMP. So the sample rate in here is the rate multiplied by the change rate in the first function. And then the SMP, we set the SMP as the shifted.wav. The final name of this, the out file, will be final.wav. So we set the sample width, the sample frame rate, the channel, and here it says here that make sure that the window size is even and larger than 16. So it is always 16 because one window size is a 16-bit. So sound is always being processed in 16 windows. So I already explained this why it's divided by 2, because it going to be half here in the part here. Window size will be half, and here is the computation of the displacement. So this stretch is the change rate written above already. The start is the 0% when you run the program, and here is the Hanning window. So this formula is a Hanning window formula. So it's 0.5 is 1/2 minus NP that cosine. The range is set to window size, the diff type is float, and multiply to 2 pi over the n minus 1, and n is the window size, then multiply to 1/2. So here also is the formula for Hanning window. And then after you create a window buffer and get the window buffer, you're going to perform the fast Fourier transform. We do the Hanning function to perform the fast Fourier transform. So here fast Fourier transform, in here in each segment it will be transformed into fast Fourier to go back to its original, and it disregards the original paces and put random paces. So the random paces is this. So there will be a frequency, there's a frequency distribution of single harmonic. So this is the distribution. It has a 256k samples, and then convert to complex number and randomize the phases. So then perform again the inverse fast Fourier transform to return its original size. So here is it. You transform to its original size, and then the range of the one window clamp into -1 to 1, and here it is the computation for the or codes for counting from 0% to 100%. So it will write in the screen of the console. So it says here that the if star pause, which is 0.0 here, is less than or equal to SMP, which is the shifted .wav. Print 100%. It says that it should be 100% already. So here is the part of Matplotlib plotting the WAV file. So I'm going to run the program to show you how it works. So now we're going to test these codes. So first, let's see. Let's play the WAV file that we use. So this is the WAV file that we used.
Calling Jollibee delivery. First press the hashtag. First press the hashtag. Don't forget the hashtag. Don't forget the hashtag. 87,000. Hashtag 87,000 Jollibee delivery. It's a bot.
So that's the original WAV file. So now let's try. So let's try the first function, pitch, and let's set it to high, which is 3. Then enter. You will see sampling rate is multiplied to 3, which result to this. So now let's play the saved shifted .wav. Let's see what happened. So as you can see, from 0.57 seconds, it becomes 0.38 seconds. So it shifted the pitch, but the time also follows, because according to the theory of pitch shifting, the time always follow the pitch. So let's call the function for stretching to go back to its original sets to 3. Now we open the file. Name of that is final.wap. So let's open that file and let's see what happened. So as you can see, from 0.38 it goes back to 0.57. Now let's try low pitch. Let's run the program again and type the first function, pitch, and now let's set the change rate into 1. There you go. And then let's hear the shifted that WAV.
Calling Jollibee delivery. First press the hashtag. First press the hashtag. Don't forget the hashtag. Don't forget the hashtag. 87000. Hashtag 87000. Jollibee delivery.
So from 0.57, it becomes 1 minute and 55 seconds for low pitch. Now let's stretch the low pitch. So let's play.
Calling Jollibee delivery. First press the hashtag. First press the hashtag. Don't forget the hashtag. Don't forget the hashtag. 87000. Hashtag 87000. Jollibee delivery. Hashtag 87000. Jollibee delivery. Don't forget the hashtag.
So it returned to 0.57 seconds again. Now let's try plotting the figures, the WAV file.